Hello everyone, welcome back to my channel. In the last video, we discussed that the complex number representation by using a J operator method, and even we discussed there what happens when the alternating voltage across a inductor and a capacitor and resistor individually. Today we are going to learn what happens when the alternating voltage is applied across the combination of inductor and resistor, capacitor and resistor, and inductor, capacitor and resistor in series. So the first one is AC circuit containing inductance and resistance in series. Inductance and resistance in series. So we are going to observe the circuit diagram for inductance like this and the resistance of a resistor which is connected across an AC source. Let L be the inductance of inductor and R be the resistance of resistor. The voltage drop across an inductor that can be represented by VL, and the voltage drop across a resistor that can be represented by VR, and I be the current flowing through that circuit. We know that the complex voltage across an AC source that can be represented by V is equal to V naught e raised to j omega t. Let us consider this one as an equation number 1. The complex voltage across an AC source is V is equal to V naught e raised to j omega t. Now the voltage drop across the inductor and resistor is the voltage drop across inductor and resistor that can be represented by VR is equal to I into R we are going to get, and VL that can be written as J into omega L into I. This we are considered along x axis, and this one is along y axis. If we observe the diagram, that is, we know that a real axis along the x axis, and imaginary axis along y axis. So this represents a resultant voltage at an angle that is pi. So along the x axis we took a VR, and along y axis we have to consider a VL, voltage across inductor. Now the total potential drop in a combination is equal to that V is equal to VR plus of VL. So we know that V in the sense the voltage across an AC source, therefore V which is equal to I into R plus of j omega L into I. So I is a common term and the remaining term is R plus of j into omega L. Now this can be written as I is equal to V divided by R plus of j omega L. Now I is equal to V is nothing but V naught e raised to j omega t divided by R plus of j omega L. Let us consider this one as an equation number 2. We know that R plus of j omega L that can be written as Z cos of pi plus of j into Z sin of pi. Now if we simplify this one, take a Z as a common term, therefore cos of pi plus of j into sin of pi we are going to get. Now R plus of j omega L, this can also written as Z we know that cos of pi plus j into sin of pi, that can be written as e raised to j of pi. Let us consider this one as an equation number 3. We know that r is nothing but, from this equation, r is nothing but z of cos of pi and omega L, in the sense omega L, which is equal to z of sin of pi. Let us consider this one as an equation number 4 and equation number 5. Squaring and adding equation 4 and 5. So we are going to get r square plus of omega square L square, which is equal to z square. Therefore z is equal to square root of r square plus omega square L square we are going to get. So here pi is the phase angle, that phase angle that can be written as tan inverse of omega L divided by r we are going to get. So if we simplify further, we are going to get from equation 2 becomes equation 2 that can be represented by I is equal to V naught e raised to j omega t divided by r plus of j omega L, in the sense here r plus of j omega L is z into e raised to j of pi. So z into e raised to j of pi. If we simplify this one, I is equal to V naught divided by z. So e raised to j omega t minus we are going to get j of pi. Therefore I is equal to V divided by z, in the sense I naught e raised to j is a common term omega t minus of pi we are going to get. Let us consider this one as an equation number 6. So now by comparing equation 1 and equation 2, so equation 1 represent V is equal to V naught e raised to j omega t, and the equation 6 represent I is equal to I naught e raised to j omega t minus of pi, and this concludes that I current lags behind a voltage, by an angle that is pi. Current behind a voltage by an angle that is pi. So we know that the phase difference, that is V is equal to V naught e raised to j omega t and I is equal to I naught e raised to j omega t minus of pi. In the sense there is a phase angle that is a pi, therefore a current lags behind the voltage by pi by 2. Based on this, we are going to observe a wave diagram. Let us consider this represents a voltage wave. V is equal to V naught e raised to j omega t, voltage or current along y axis and along z axis, x axis is omega t, and this represents a current wave I is equal to I naught e raised to j omega t minus of pi. And if you observe the phasor diagram for this one is, this one is on a real axis we know, and this represents imaginary axis. Let us consider, and this is a voltage across a resistor, and perpendicular to this one is voltage across inductor. We know that the resultant of these two, we are going to get the peak value of voltage, that can be represented in this form. So this is omega t, an angle between the peak value of voltage, the not value, and angle between a voltage and the current, that can be represented by pi. Therefore we are going to observe there is a phase difference angle omega t minus of pi, and this is the phasor diagram for a circuit containing inductance and resistance in series. Next concept is AC circuit containing capacitance and resistance in series. Capacitance and resistance in series. For that we are going to observe a circuit diagram. Let us consider this one is a capacitance and this represents a resistance. They are connected in series, and these two they are connected across an AC source. Capacitance of the capacitor that can be represented by C, and resistance of a resistor that can be represented by R. So here VC is the voltage across a capacitor and VR that represents the voltage across a resistor. We know that the complex voltage across a AC source, the complex voltage across AC source that can be represented by V is equal to V naught e raised to j omega t. Let us consider this one as an equation number 1. Now the potential drop across a resistor and capacitor, the potential drop across resistor and the capacitor, that becomes VR, which is equal to I into R, and VC, which is equal to I naught divided by j omega c. Now this can also written as VC, which is equal to minus of j I divided by omega c. This is not I naught I. Now the total potential drop across the combination of capacitor and resistor, that can be written as total potential drop across combination of capacitor and resistor, that can be written as V, which is equal to VR plus of VC. We know that V, which is equal to VR in the sense I into R, therefore minus of j I divided by omega c. If we simplify this one, V is equal to, take I as a common term, therefore R minus of j divided by omega c we are going to get. So if we simplify this one, I is equal to V divided by R minus of j divided by omega c we are going to get. We know that I is equal to V in the sense V naught e raised to j omega t divided by R minus of j divided by omega c. Let us consider this one as an equation number 2. Now we know that R minus of j divided by omega c, that can be written as z cos of pi minus of j z sin of pi. Now z into cos of pi minus j sin of pi. Therefore R minus of j divided by omega c, that can be written as z into e raised to j of pi. Even R can be written as R is equal to z cos of pi and 1 divided by omega c, which is equal to z sin of pi. So let us consider these two equations, R and 1 divided by omega c. If we squaring and adding these two expressions, we are going to get z is equal to, or z square is equal to R square plus of 1 divided by omega square c square, and here z is equal to square root of R square plus of 1 divided by omega square c square, and this expression that represents the impedance of AC circuit. Equation 2 becomes I is equal to, equation 2 becomes I is equal to V naught e raised to j omega t divided by, in the place of R minus of j divided by omega c, if we consider z is equal to e raised to j of pi. So R minus of j divided by omega c, that can be written as z cos of pi minus is there, therefore we are going to get a minus sign here, so it becomes a minus. Here this expression that becomes a V is equal to V naught e raised to j omega t divided by z, and e raised to j omega t if we take in the numerator, therefore we are going to get plus of j of pi. Therefore I is equal to V naught divided by z in the sense I naught e raised to, take a j as a common term, and the remaining term is omega t plus of pi we are going to get. And let us consider this one as an equation number 3. And we know that the phase difference that is pi between the alternating voltage across an AC source and the current through that circuit, that can be written as V is equal to V naught e raised to j omega t, and I is equal to I naught e raised to j of omega t plus of pi. Here this represents that current leads voltage by an angle that is pi, and we know that the phase angle that can be written as pi, which is equal to tan inverse of 1 over omega c divided by r. And if you observe the wave diagram for the voltage and the current, let us consider this is a voltage wave. V is equal to V naught e raised to j omega t, along the x axis we took omega t, and this represents the current wave, and its value becomes I is equal to I naught e raised to j into omega t plus of pi. And this is the wave diagram for voltage and current in the combination of capacitor and resistor. If you observe in Phasor diagram, let us consider along x axis we took a real axis, along y axis is an imaginary axis. So here this represents a voltage across a resistor, and this one represents a voltage across a capacitor, and the resultant voltage of these two, we are going to get the peak value of a voltage, that is V naught. Let us consider, and this is an omega t, and this represents the angle that is pi, the phase angle. So here it is 90 degree. Therefore we are going to get the current in the circuit is I is equal to I naught e raised to j into omega t plus of pi, here omega t plus of I. This represents AC circuit containing a capacitance and resistance in series. And the next concept is AC circuit containing L, C and R in series, inductance, capacitance and resistance in series. So we are going to observe the circuit diagram for the series combination of inductance, capacitance and resistance. Now we know that the AC alternating voltage across AC source, that can be represented by V is equal to V naught e raised to j omega t. Let us consider this one as an equation number 1. And even the potential drop across inductor, capacitor and resistor, that can be written as VR, which is equal to I into R, VL, which is equal to j omega L into I, and Vc, which is equal to minus of j into I divided by omega c. Now the total potential drop in the circuit that can be represented by VL plus of VR plus of Vc, which is equal to that voltage across a AC source. So here VL is nothing but j omega L I plus of VR in the sense I into R plus of, here it is the Vc in the sense minus of j I divided by omega c, which is equal to V naught e raised to j omega t, because we know that V is equal to V naught e raised to j omega t. Now take I as a common term, therefore we are going to get j omega L plus of R minus of j divided by omega c, which is equal to V naught e raised to j omega t we are going to get. Now this can be written as I is equal to V naught e raised to j omega t r plus of j into omega L minus of 1 divided by omega c. If we simplify this one, we are going to get this equation. Let us consider this one is an equation number 2. We know that r plus of j into omega L minus of omega c, which is equal to z cos of pi plus of j into z sin of pi. Now z into cos of pi plus j into sin of pi, that we have to consider as z into e raised to j of pi. And we know the value of r, where r is equal to z cos of pi and omega L minus of 1 divided by omega c, which is equal to z sin of pi. So if we squaring and adding about these two equations, we are going to get z square is equal to r square plus of omega L minus 1 divided by omega c whole square. Therefore z that can be written as r square plus of omega L minus of omega c square root of r square plus omega L minus of 1 divided by omega c. Z represents the impedance in that circuit. Now equation 2 becomes here I is equal to V naught e raised to j omega t divided by r plus of z into omega L minus of 1 divided by omega c, that can be represented by z e raised to j of pi. We are going I is equal to V naught divided by z is nothing but I naught. So if we simplify, e raised to j omega t minus of j pi, we are going to get I is equal to I naught e raised to j is a common term omega t minus of pi, we are going to get. Let us consider this one as an equation number 3. If we compare equation 1 and equation 3, that I lags behind a voltage by a pi value. So if you observe a phasor diagram for AC circuit containing inductance, capacitance and resistance in series, let us consider a VR is the voltage across a resistor and VL voltage across an inductor and VC voltage across a capacitor. We know that the angle between voltage across an inductor and voltage across a resistor is 90 degree, and even the voltage across a resistor and voltage across a capacitor is 90 degree. Here it is a inductive oriented circuit, therefore we are going to get a value that is VL minus of VC, and the resultant voltage of these three that can be represented by a V naught. So peak value of voltage, and the angle between a V naught and along x axis we took as a omega t. The angle between the resultant voltage V naught and voltage across a resistor that can be represented by pi, and this represents the lags behind the voltage by the pi by, and this is about a phasor diagram for AC circuit containing inductor, capacitor and resistor. If you like my content, please subscribe my channel and click on bell icon. Thank you.